Okay, good morning, everyone. Welcome back. So today we will continue our discussion about the special relativity. So in the previous lecture, we first did some review about 3D space. We showed that in 3D space, based on the rotational symmetry, based on how system responds, how physics quantities responds to coordinates rotation, we can classify physics quantities into scalars, vectors, rank 2 tensor, rank 3 tensor, etc. Okay? So this classification tells us immediately how each physics quantity responds to rotation. Okay? We know the rotational matrix, and we can write down their rotation. Well, how do they do? What do they do under rotation? And more importantly, the reason we want such a classification is because this classification enables us to guarantee that the physics law are independent of orientations of the coordinate axis. Okay? As long as our physics law can be written in the forms of scalar equals scalar, vectors equals vector, tensor equals tensor, etc. As long as we follow this rule, we can guarantee that all those physics laws stay exactly the same, no matter how we rotate the axis, no matter how we choose the direction of the axis. Okay? That's the way to guarantee that our physics law are independent of rotations, independent of choice of axes. Okay? And then we went to 4 dimension, and we showed that in 4 dimension, the Lorentz boost and the 3D rotation together, combined together, gives us actual rotations in 4 dimension, okay, in 4-dimensional space-time. So we can combine Lorentz boost, we should think Lorentz boost as a 4-dimensional rotation, and then combined with 3D spatial rotations, we get a rotational group for 4-dimensional space and time. Okay. So this 4-dimensional space and time rotation is very similar to our 3D rotation, except that now in the definition of length, or more precisely the square of length, we have both plus sign and minus sign. The time direction contribute plus sign and the spatial direction contribute minus sign. So in 3D space, all of them are positive, but in 4D space-time, we need to assume one of them contribute a positive sign, the rest 3, the spatial direction contributes to the negative sign. But nevertheless, this Lorentz boost still behaves like a 4-dimensional rotation. Okay? And then, if we want our physics laws to be the same, to take the same form, independent of choice of reference frames, or stay the same form under Lorentz boost, then we have to do the same as what we did in 3D space. Okay? We need to classify physics quantities into 4D scalars, 4D vectors, and 4D rank 2 tensor, 4D rank 3 tensor, etc. Okay? And we have to make sure that all our physics laws is written in the structure of scalar equals scalar, vector equals vector, tensor equals tensor. Okay? As long as we have this structure for our physics laws, we can guarantee that under spatial rotation and the Lorentz boost, our physics law stays the same. Okay? Because Lorentz boost takes us from one reference frame to another reference frame, this structure guarantees that all different reference frames sees exactly the same physics law. Okay? So that is one fundamental assumption, and that assumption is called the principle of special relativity. And special relativity tells us for all reference frames, we should see exactly the same physics law. And mathematically, this means all physics laws, we have to be able to return any physics law in this structure I mentioned. Scalar equals scalar, vector equals vector, tensor equals tensor. Okay? If one side of my physics law is a scalar, the other side is guaranteed to be a scalar. If the other side is not a scalar, then this equation, this physics law, will not take the same form under Lorentz boost. In other words, one reference frame and another reference frame will see different physics laws. That was assumed to be not allowed. Okay, so that was the principle we discussed last time. Last time we defined 4D scalars and 4D vectors. So 4D scalar basically is an object that invariant under 4D rotation, which means it is invariant under Lorentz boost and is also invariant under spatial rotation. Okay. And we also defined 4D vectors, and the 4D vectors is defined as follows the transmission of coordinates. Okay, so coordinates is the first vector we define, and we know the coordinate under 4D rotation, say Lorentz boost, it follows this transformation. Okay, so if we have another 4 numbers organized together, and the other 4 numbers follows the same transformation under Lorentz boost and under spatial rotation, then we call it a 4D scalar, 4D vector. So 4D vectors are objects that follow the same transformation as coordinates. Okay. And we gave you one example towards the end of last lecture. So towards the end of the last lecture, we showed that the spatial derivatives, partial time, partial x, partial y, partial z, can be organized into a 4D vector. Okay. And interestingly, if we naively organize these 4 things together, it's not a 4D vector. It's very close to a 4D vector, but it's not quite. Because it obeys the inverse Lorentz boost, not the Lorentz boost. So this object transforms exactly the opposite of coordinates. Okay? So in order to make sure the derivative transforms the same way as coordinates, we made a small trick. We add a negative sign for the spatial component. And with this minus sign added, these 4 objects combined together, their transformation is exactly the same as coordinate. For example, the Lorentz transformation takes exactly the same structure. So this is our 4D vector for the derivative, 4D derivative vector. Okay, so that's one 4D derivative, 4D vector we demonstrated as an example in the previous lecture. And in principle, any physics quantities, as long as you can organize them in this structure, and as long as under Lorentz boost and spatial rotation, it behaves the same as coordinates, we will call it a 4D vector. Okay, so that is one example we discussed last time. And towards the end of last lecture, we also briefly mentioned the terminology of contravariant vectors and covariant vectors. Contravariant vectors means it behaves the same way as coordinates. That's what we call the vectors. Okay. Covariant vector means that it behaves almost like a vector, but it obeys the inverse transformation. Okay. So in this sense, the naive combination of the space-time derivatives, this is a covariant vector. And with the proper minus sign added, it becomes a contravariant vector. And covariant and contravariant vector is it is a terminology that must be used, the concept must be used in general relativity. In special relativity, they are not necessary. And in our lecture, we will try not to use these 2 terminologies. We will try just to be simple, just use vectors. Okay. But if you are majoring in theoretical physics, or if you are going to study special relativity, special relativity, quantum physics, quantum field theory, or general relativity, this language, I strongly recommend you to try to get familiar with this language. And this will be essential and very useful for future courses. Okay, so for this course, we will not require you to learn this, we will not require you to utilize this terminology, but for future courses, if you want to study theoretical physics, then this is a very useful terminology that one has to learn. Okay, and for this related with this terminology, if you are using contravariant and covariant vectors, contravariant vector usually we put the index xyz t index above the vector. Okay, so if you see a superscript, it means it's a contravariant vector, and if you see a subscript, it means a covariant vector for most literature. Okay, so that's a terminology issue, and we briefly mentioned last time. Oh, one final thing we mentioned last time is that from the derivative 4D vector, we immediately get another 4D vector, which is the frequency and the wave vector. Okay, the frequency and the wave vector with this specific combination must also be a 4D vector. The reason we know that is because for a plane wave, this derivative becomes omega and k. Okay. And because this is a 4D vector, this omega and k must also be a 4D vector. Okay, and this 4D vector is actually very useful because we know this is a 4D vector. Immediately we know how it transforms under Lorentz boost. Okay, because it's a 4D vector, it transforms under Lorentz boost exactly the same as x and our coordinate. Okay, it follows exactly the same transformation under x. So as long as so once we realize this is a 4D vector, immediately we can write down its Lorentz transformation. It's exactly the same as coordinates. Okay, and in your homework this week, you are utilize the fact that this is a 4D vector, so it follows the same Lorentz transformation as coordinates to prove a couple conclusions. Okay, and it turns out once we know this guy is a 4D vector, we can immediately write down the transformation, and from the transformation, we can actually learn a lot of things. Okay, that is one practice you are seeing in this week's homework problem. Okay, so that's a summary about the previous lecture. So today we will conclude our discussion about math and then go back to physics. Okay, it turns out we need to introduce one more terminology in math before we can go back to physics. That's the so-called inner product. Okay, so the inner product is a product of two vectors. And the inner product, as you probably already know, same as 3D Euclidean space, inner product give us a scalar. Okay, so mathematically, inner product is a mapping, and the input are two vectors, and the output of this product is a scalar. So utilizing two vectors, multiply them together, and get a scalar. That's the so-called inner product. Okay, so oops, let me write something. Okay. So in 3D space, in 3D Euclidean space, we know the inner product is very easy. Okay. Oops. Let me try to get to the pencil work. Okay. So suppose we have vector, say A, which has three components: AX, AY, and AZ. Okay. So this is a 3D vector in 3D space. And suppose we have another vector B. This is BX, BY, BZ. Okay. The inner product of A and B is A dot B, which is AX BX plus AY BY plus AZ BZ. That's the definition of inner product in a 3D space. Okay, so this inner product can be rewritten in a matrix form: AX AY AZ, which is a row vector, and I will write BX BY BZ as a column vector. So the multiplication of a row vector and a column vector together is its inner product. That's another way to understand the inner product. There is a third way to understand the inner product. That is the same thing, but I add the identity matrix in the middle. Okay. So this identity matrix in the middle don't do anything. So it's still A vector times B vector. It's still the inner product. It's still the same thing. Okay. So what we are going to utilize is this third picture, the last picture, to understand the inner product. Okay. So inner product is a vector multiplied with the other vector, but with a matrix in the middle. And this matrix is what we call the metric tensor, the metric tensor. And in 3D Euclidean space, the metric tensor is 1, 1, 1. It's identity matrix. But in 4D space, we know the metric tensor is not 1, 1, 1. It's +1 for time, -1, -1 for space. Okay. So in the 4-dimension, inner product is defined this way. If we have a 4-dimensional vector x, a 4-dimensional vector y, okay, and we want to construct the inner product between these two quantities, what we need to do is we need to do this. We have the x vector, we have the y vector. One of them is column vector, one of them is the row vector, another is column vector, and we multiply the metric tensor in the middle. Okay, and we can write down this multiplication, this matrix multiplication, very straightforwardly. It's very similar to 3D inner product. It's the first component multiplied together, second component multiplied together, third component multiplied together, last component multiplied together. The only difference is in 3 dimension, we add the multiplication. We add this multiplication, all different components. But in 4D, we add the zeros component. Then we subtract the first, third, second, and the third components. And the reason of this minus sign is because our metric tensor is 1, -1, -1, -1. That's the same minus sign. Okay, that's the definition of inner product for the Minkowski space for special relativity. Okay, and one can easily verify that this inner product of two vectors indeed gives you a scalar. Okay, before we prove that, let's first look at the example. Okay, one example we are very familiar with is actually distance. Okay, if we have two events A and B in a 4D space, then the separation between A and B is described by a 4D vector. Delta T is the separation along time. Delta X and Y and Z are the separation along X and Z and Y and Z axis. Okay, this is the distance in space. This is the displacement in, this is the distance in time. The last three components are the displacement in space. So this is a 4D vector. Okay, and this 4D vector, if we calculate the 4D vector inner product to itself, this 4D vector multiplied by itself with metric tensor in the middle, then we get the 4D distance we discussed in the last time. And the 4D distance is a scalar because we know this 4D distance is invariant under Lorentz boost. It does not change. Okay, so this is one example where the inner product of two vectors gives you a scalar. So this vector changes under Lorentz boost according to Lorentz transformation. But the inner product, L square, is invariant. Whatever reference frame we're using will get the same L square. Okay, it does not depend on Lorentz transformation. Okay, so this property is very similar to the inner product of two 3D vector. The 3D vector, the inner product is a scalar. Okay, once you do the inner product, the scalar does not change anymore when we rotate the axis. Okay, and so the most important property, or the first property of inner product I just already mentioned, if you have two vectors and we compute the inner product, it's a scalar. Okay, so here is a detailed proof. Okay, to prove that, we just need to do the transformation. Okay, suppose this is x and y components in one reference frame. Now let's go to a different reference frame. In a different reference frame, y becomes y prime, x becomes x prime. Okay, and because this y and x are vectors, we know how does vector transform. Okay, vectors transform same as coordinate. Okay, so how do they transform as how does coordinate transform? The coordinate transform through a rotational matrix, and this rotational matrix is a 4D rotation, and it's the same rotational matrix the coordinate use. Okay, it's the same rotation the coordinate use. And for the x vector, it's the same thing, but because x vector is a row vector, it's a transpose of a column vector. The transformation matrix also gets a transpose here. Okay, and as we showed earlier in the previous lecture, if we have a rotational matrix of this 4D rotation, transpose times metric tensor times 4D rotation, 4D rotations preserve the metric tensor. Okay, so metric tensor actually doesn't change under 4D rotation. So RT times G times R must be the same as G. And the metric tensor is invariant under rotation. This is the same as saying the distance is invariant under rotation. And distance should be invariant under rotation. That's the definition of rotation. Okay? So for 4D rotations, no matter what rotations we are considering, this thing in the middle, RT times metric tensor times R, is just a metric tensor. Okay, so this whole thing is just a metric tensor. If we replace this thing in the middle as a metric tensor, we find that this is the inner product of x and y. So in other words, the inner product of x prime and y prime equals to the inner product of x and y. And the reason is because the rotations in 4D space, or in any space, rotations by definition should not change the metric tensor. And because metric tensor stay invariant, the multiplication, the inner product should stay invariant. Okay, so this is actually the same as saying inner product of two vectors in 3D gives me a scalar. In 4D, it's exactly the same story. Okay, the only complication is here the metric tensor is a little bit more complicated, but the proof is exactly the same as 3D space. Okay, so that's the first and the most important property of inner product. Two vectors, inner product, I got a scalar. And another important property of inner product is exchangeable. Okay, so in other words, x times y is the same as y times x. So for number product, we know the product of two numbers, we can always switch the order. Let's say 1 times 3 is the same as 3 times 1. But for matrices, or for vectors, or for more complicated algebra objects, multiplication not necessarily are exchangeable. Sometimes it is, sometimes it's not. And the most famous example is probably, well, the example we are most familiar with is probably the quantum mechanics. Quantum operators, they don't commute with each other. We can't switch the order. Okay? It turns out for inner product, you can always switch the order. X times y is the same as y times x. Okay, so I will not bother you with the detail. By the way, this is true as long as the metric tensor is a symmetric matrix. And metric tensor usually will assume it's a symmetric matrix. So as long as the metric tensor is symmetric matrix, inner product of xy and yx are always the same. And for the metric tensor we are using here, it's obviously a symmetric matrix. So xy and yx, the inner product, are the same thing. To prove that, it's quite straightforward. Okay, we just need to take a transpose. Okay, if we take a transpose, we can show that x transpose times x times y and y times x are exactly the same thing. Okay, so I will not go into the detail. Okay, so you can look at the detail afterwards by looking at the lecture notes. So basically, we just take a transpose of this thing, because the inner product is a number, it's a scalar. Transpose of a scalar, transpose of a number is still the same number. Okay, so for a number, we take transpose, it's still the same number. For a matrix, the transpose gives you a different matrix. But if you only have a number, 1 by 1 matrix, transpose is the same as no transpose. So they are the same. And when we take the transpose of 3 objects, what we need to do is to reorder the 3 objects, put the last one to the front, so y to the front, x to the end, and the g in the middle. Okay, so take this is a property of transpose. If you have a product of several objects and take transpose, the transpose will switch the order. And then we take the transpose of every single object. Y becomes y transpose, G becomes G transpose, and X transpose become X transpose transpose. X transpose transpose is just X, because 2 transpose, it means nothing, means doing nothing. Okay, and we utilize the fact that G transpose is same as G, assuming G is a symmetric matrix. So the transpose and the no transpose are the same. Then we prove that X times Y is the same as Y times X. Okay, so this is another very important property for inner product. Okay, and if we want to write down the components of this matrix, of this product, this inner product can also be written in terms of the components of X and Y, and it can be written like this. Okay, X subindex mu can be 0, 1, 2, 3. Y subindex mu can be nu can be 0, 1, 2, 3. Okay, and the matrix tensor has subindex nu. One of them is same as X. The other one is the same as the index of Y. And G mu nu can be 0, 1, 2, 3. And this is a 4 by 4 matrix. Okay, so this is a component way to write down the inner product. Okay, so finally, before we go to the next part, let me briefly mention about the covariant and the contravariant conversion. Okay, so again, this is not required. If you don't want to learn this terminology, you can skip this part. But if you want to practice and want to get familiar with this terminology, and here is a comparison between our convention, which don't use covariant vector. We only use contravariant vector, and we call it vector. Okay, if we use covariant and the contravariant vector convention, X and Y, what we call vectors are in fact contravariant vectors. So contravariant vectors are objects the same as coordinates. Okay, and according to the convention, contravariant vector should use upper indices. Okay, so for our X and Y, we should use upper indices. And for metric tensor, the metric tensor should use lower indices. Okay, our metric tensor 0, -1, -1, -1 actually has 2 lower indices. Okay? And one important rule in this contravariant and covariant terminology is that when we multiply 2 objects, the repeating index must obey one is a higher one is a superindex, one is a lower index. Okay? So in the covariant and the contravariant language, we can't multiply 2 objects where mu and nu are both subindices. Now we can't multiply them. We need to make sure one is above, one is a superindex, another one is a lower index. So that is a convention in the contravariant and the covariant structure. Okay, so and that one is achieved by making the G has lower indices, where the vectors has higher indices. Okay? And another useful thing in this contravariant and covariant language is that for any contravariant vector, say Y, okay, so this is a contravariant vector because the index is high, is a super index. Okay, for any contravariant vector, we can utilize the matrix tensor to define a corresponding covariant vector. Okay, so this Y sub mu is a covariant vector. As you can see, the index is a lower index, it's not an upper index. Okay, and this lower index is obtained by doing this. Okay, I multiply a matrix tensor with my vector, with my contravariant vector. Okay, so the matrix tensor has 2 lower indices. One of them, I choose it to be the same as my upper index nu. Okay, and according to Einstein convention, this nu we need to sum over this nu. Nu can be 0, 1, 2, or 3. I take all the first possibilities and I add them up. This is Einstein convention, as we mentioned earlier. So once this mu index is summed over, the mu index is gone. I consider all of them and I sum them all together. but I only have one index left. That's this mu index. And this mu index is the lower index, and that gives me a covariant vector. Okay. If we define the covariant vector in this way, okay, then the inner product, we can write it in a different way. So the inner product, the same inner product I defined here, we can write it as x mu, y mu. X is the contravariant vector with superindex. Y is the covariant vector with lower index. Okay, so in this contravariant and covariant language, inner product is not between two vectors. It's between one covariant vector and one contravariant vector. One has higher index and one has lower index. As I mentioned earlier, when we do the multiplication in this language, in this convention, one need to have higher index, another need to have lower index, and that is the example. One has higher and one has lower. This is the inner product. It's easy to check that this structure is exactly the same as what we had before. Okay. Remember this y sub mu is actually metric tensor times y. If we replace y sub mu by metric tensor times y, then we come back to exactly the original definition we have. Okay. So in some literature, you may notice that the inner product is defined this way. And if the inner product is shown this way, you understand immediately it's the same thing as what we are doing here, except that that literature is using the covariant and the contravariant terminology. Okay. So in the covariant contravariant terminology, the inner product is much shorter. We only have x, y. We don't need to write down the metric tensor. But in reality, the metric tensor is there because we need to use the metric tensor to define what is y sub mu. Okay. Anyway, so this is just a terminology issue. And for this inner product terminology, we can show that x mu and y mu, x superindex, y and subindex is the same as x mu and y mu if x has lower index and y has upper index. And we can also prove that if we swap x and y, switch order, is still the same. Okay. So the bottom line, we can define inner product in the 4D space, and this inner product allows us to build a scalar out of two vectors. And two vectors, now we immediately build a scalar. Okay, let's give a couple examples here. Okay, so right now we know two examples of 4D vectors. One is my coordinate, time and space. Okay, that is a 4D vector. We already know that. Okay, that's actually the definition of 4D vector. Everything transforms the same way as this coordinate is called the 4D vector. Okay, and we also showed in the previous lecture, derivative with proper minus sign added is a 4D vector. So this is a 4D vector. This is a 4D vector. That's pretty much the only two 4D vector we know right now. Okay, and if these two are two 4D vectors, the inner product should be a scalar. Okay, so let's compute the inner product of this vector, derivative vector, with coordinate vector. Is that a 4D scalar? Is that a scalar? Well, this is actually a straightforward multiplication. If we multiply this together, it's just this guy. Partial 0 x0 plus partial 1 x1 plus partial 2 x2 plus partial 3 x3. Okay, you may see some minus sign here in the derivative. You may also see some minus sign here in the metric tensor. The metric tensor minus sign and the derivative minus sign precisely cancel each other. So at the end of the day, everything is positive. It's a very straightforward multiplication problem. And this object obviously is 4, okay? Because the derivative to itself, the quantity to derivative to itself is 1. And I have 4 of them add up together is 4. This one is obviously a scalar. No matter what coordinate we choose, no matter what reference frame we choose, this is mathematically defined to be 4. Okay, so indeed, inner product of the two vectors we know gives me a scalar. And this 4 is a scalar independent of reference frames. Okay, and another example is inner product of derivative to itself. Okay, we know derivative is a vector, as we showed in the previous lecture. Okay, and so we have vector and itself, inner product. This one should also give me a scalar. Okay, and what is this scalar? Okay, and by definition, the inner product of derivative to itself is this guy. And if we multiply these vectors with matrices and write it out, it's the time derivative square minus spatial derivatives. Okay, this is the second order derivative. And this second order derivative is a 4D version of Laplacian. Okay, Laplacian is a 3D scalar. It's the inner product of 3D derivative to itself. And this guy is a 4D version of Laplacian. It has a name. It's called the I don't know the proper pronunciation. Sorry for that. The Allenbert operator. Okay. So nevertheless, this operator is a scalar. It's a 4D scalar, and usually we use a square to represent this scalar, 4-dimensional scalar second-order derivative operator. It's a 4D generation of the Laplacian. Okay. Let me demonstrate one more example. Okay, we do know one more 4D vector. That is the frequency and the wave vector. Okay, so we get this towards the end of the last lecture. Okay, because if we take derivatives to a plane waves, this derivative becomes omega and k. So if the derivatives is a 4D vector, this omega k must also be a 4D vector. So this is a 4D vector. Okay, we know this omega and k gives me a 4D vector. And if this is a 4D vector, we can calculate the inner product of this 4D vector with itself. And this guy should be a scalar. Okay, and is that true? Let's look at this. This is a 4D vector multiplied by metric tensor and itself. And this is the inner product. The inner product should be a scalar. And this inner product is, if we calculate it, it's omega square minus speed of light, k1 square minus speed of light, k2 square minus speed of light, k3 square. This one indeed is a scalar, and it has a very clear physical meaning. It's obviously a scalar. The reason we know this is a scalar is because this guy is nothing but the rest mass of the particle and the rest mass of the object. And the rest mass of object is independent of reference frame. Okay? In different reference frame, the mass of object could be different, but the rest mass is always the same. Rest mass is the intrinsic property of a particle. That's a mass where we measure the mass of this particle when this particle is not moving. Okay, so that one is independent of reference frame. And to see this one is rest mass, it's actually we need to use particle wave duality from quantum mechanics. Okay, so in quantum mechanics we know particles are waves and waves are particles. Okay, and if we have a wave with frequency omega and the wave vector k, this wave gives me particles, quantum particles, and the energy of a quantum particle is h bar omega. Okay, that's what Planck told us. H bar is the Planck constant, and momentum of my quantum particle is h bar times k. Okay, so let's multiply h bar square for this object for every single term. Okay, if I multiply every term by h bar square, h bar is a physics constant. H bar is a scalar. So scalar multiplied by scalar should also be a scalar. Okay, so if I multiply h bar square multiplied by frequency square become energy square. And the wave vector multiplied by h bar becomes momentum. So I get momentum square in the x direction, momentum square in the y direction, momentum square in the z direction. And the c is the speed of light. We still have c. Okay. So the bottom line, this whole thing, if we multiply Planck constant square, we get energy square minus speed of light square times momentum square. And this is the definition of rest mass. Okay. Remember, the energy of a relativistic particle is momentum square plus speed of light, multiply speed of light square, plus rest mass square multiplied by speed of light to the fourth power. Okay, so that's the definition of energy for relativistic particle. From this energy, if we take a square and massage this formula a little bit, one can immediately prove that energy square minus p square c square is rest mass square multiplied by a physics constant, speed of light to the fourth power. Okay. So this object is actually rest mass multiplied by some physics constant speed of light. So the bottom line, this inner product of frequency wave vector 4D vector, the inner product to itself gives us a rest mass. And the rest mass is a scalar. Actually, more precisely, it's rest mass times multiplied by some physics constant like speed of light and Planck constant. Rest mass is a scalar. Physics constant like Planck constant, speed of light are also fundamental, are also scalar. Does not change from one reference frame to another. So this whole thing must be a scalar. So indeed, the inner product of this vector to itself also gives us a scalar. Okay. So inner product of any two vectors must be a scalar. And here it is a scalar because it's just rest mass. Okay, so that's all the mass we need to know about 4D space. Now let's go back and look at physics and look at the dynamics of special relativity. Okay. So in this chapter, the ultimate goal that we are going to prove and we're going to show is that how does Einstein know energy need to be mass times speed of light squared? Okay. It turns out to get this conclusion, we don't need to do much work. Okay. The only assumption we need, actually, there are only two assumptions we need. One is what we already discussed a long time ago in the first chapter. Okay. We need to assume speed of light is defined for the observers. So all observers, no matter which reference frame, see the same speed of light. And from there, we know Lorentz transformation, blah, blah, blah. And the second assumption we need is that we need to assume all different reference frames see exactly the same physics law. Okay, so the physics law remains the same for all different reference frames. In other words, there's no special reference frame. All reference frames are equivalent to each other. They give the same physics law. And from the second chapter, we know mathematically that means all physics laws need to be written in the structure of scalar equals scalar, 4D scalar equals 4D scalar, 4D vector equals 4D vector, 4D tensor equals 4D tensor, etc. Okay. Basically, by using only these two assumptions, speed of light is to the observers, and all reference frames have the same physics laws, we can actually get to the conclusion E equals mc squared, and there's no other option. So that's what we're going to do. Okay, so let's look at how exactly what we do here. Okay, so to get started, let's first look at some physical quantity or some physical quantity we know. For example, we already figured out spatial derivative and the time derivative forms a vector, a 4D vector. Okay, now let's look at the so-called continuity equation. Okay, start from continuity equation. Okay, so the continuity equation we already learned from ENM1. It looks like this. Okay, it has a time derivative for the charge density and some spatial divergence of the charge current. And when I add them together, it should be 0. Okay, so what is continuity equation? Okay. So continuity equation actually means two things. First of all, it means charge conservation law. And secondly, it means the principle of locality. Okay, so in most textbook, you probably will see people say that continuity equation means charge conservation law, and vice versa. Okay, that statement is just partially correct. Continuity equation and the charge conservation law are not the same. They are slightly different. They are very much related, but they are slightly different. And the difference between them is the principle of locality. Okay, let's take a closer look. Let's take a closer look. How do we get the continuity equation, or where does this continuity equation comes from? First of all, indeed, continuity equation comes from the charge conservation law. Okay, we need to assume our charge is a conserved quantity. Electric charge is conserved quantity. So in other words, charge cannot be created or removed from nowhere. Okay, if we see an object with charge increasing, this increasing charge must come from somewhere. Okay, so let's consider an example. Suppose I'm considering an area. So this is my area. Okay, this is the 3D area. Okay, and I'm looking at the charge inside this 3D box. Okay. And what is the total charge inside this 3D box? And more precisely, what I'm looking here is the time variation of the charge inside this area. Say in the time window t to t plus delta t. Okay, so delta t is a very small time scale. So in a very small time window, I assume that the charge inside this box increase by delta q. Okay, I somehow get more charge in my system in this small time window, and this more charge is delta q. And because charge is conserved, if I have more charge in this area, it cannot come from nowhere. There are only two possibilities. One possibility is some charge from outside comes into my system through the boundary. Okay. Okay. So I have an area, some charge may flow into the area and go through the boundary. Okay. That contribution is easy to calculate. That's just total current. I is the total current through the boundary, okay, times delta t. Okay. Current is the charge that goes through some cross section per unit time, and current times time delta t is the total current, total charge that goes through the boundary. Okay, so this delta q The first contribution is charge goes through the boundary. Okay. But there is another possibility. Another possibility is the so-called teleport. Okay. So teleport means I have some charge, far away from my system, and suddenly this charge poofs away, disappeared, and teleported into my system. Okay. So it's jumped from somewhere far away into my system without going through the boundary. Okay. So the difference between teleport and go through under the first current mechanism is this teleport mechanism do not go through the boundary. It's jump from somewhere far away into my system. Okay, that's the so-called teleport. Okay. So charge conservation law do not prohibit teleport. Charge conservation law tells me my change of current need to be the summation of these two contributions. Okay, I can have charge go through the boundary. I can have teleport, and when I add these two contributions together, it's a charge change, charge variation of my system. Okay, so that's the charge conservation law. Continuity equation is a little bit different from charge conservation law. Continuity equation also assume the principle of locality, which we emphasize multiple times in the earlier part of the lecture. The principle of locality tells us an object can only influence its neighbor, its immediate neighbor. It's impossible for an object, for an event, to have an impact for something happened really, really far away. Okay? Information can gradually propagate. Okay? Or say charge can gradually move from point A to point B, but the charge cannot teleport from one point suddenly to a point far away. Okay? So this principle of locality tells us teleport is not allowed. Okay? That is an additional constraint in addition to charge conservation. Let me emphasize again. Charge conservation itself do not prohibit teleport. Okay? It's a principle of locality that said teleport is not allowed. Okay? Charge conservation law itself allows the possibility of teleport. But once we add the assumption of, once we assume the principle of locality, that term is gone. Okay? And when the principle locality is assumed, this additional teleport term is gone. That is the continuity equation. Okay, so that's why I said earlier on, continuity equation is not charge conservation law. It's almost charge conservation law, but we need to add one additional assumption, which is the principle of locality. Okay, and the principle of locality is a very important assumption, very important hidden assumption that's hidden behind almost all the fundamental principles of physics. Okay, nevertheless, let's assume the principle of locality. If you assume the principle of locality, teleport is gone. What we have is a simple formula, delta Q equals to I times delta T. Okay. Now let me divide delta T to the other side. If I divide delta T to the other side, this is what I get. Okay. Delta Q divided by delta T is the current I through the surface. Okay. Let's look at this formula. Okay. This guy. Okay. I have delta Q divided by delta T equals current. And that from charge conservation plus the principle of locality. Okay. Let's first look at the left-hand side. Left-hand side is a time derivative of charge. And we know the charge is a spatial integral of charge density. Okay. Q is a spatial integral of charge density. And if we take a time derivative, then we take time derivative. Okay. So time derivative of charge density, then do a spatial integral. That's the time derivative of charge. That's the left-hand side. The right-hand side is a total current that goes through the surface. Okay, total current goes through the surface is the current density for every point on the surface. Do an integral over the surface. Okay, so this is the current density. If I have current density and I integrate over the entire surface, I get the total current that goes through the surface. Okay. Oh, sorry, I forgot the minus sign. Sorry, my bad. There is a minus sign. There should be a minus sign here. Okay, and this minus sign actually means if I want to increase the charge, the current should go inside the system. But according to the typical convention, current density J, the positive direction of J is pointing outside of my system, That's the convention. And that different direction gives me additional minus sign here. Yeah, sorry, I forgot to highlight this, this minus sign. Okay, and this minus sign basically means I want the current to go into the system, but the positive direction of the current density, according to the typical convention, is going out of the system. Nevertheless, we have this minus sign here to keep track of the proper direction of charge flow. Okay, and for the right-hand side, this is a surface integral of current density. We can use the Stokes theorem. Using the Stokes theorem tells us if we have a surface integral of something, we can convert this surface integral into a 3D bulk integral. But instead of J, we should do the divergence of J. Okay? The divergence of J in the bulk, doing an integral, Stokes theorem tells us it's equals to the surface integral of J, current density. Okay? So this is a Stokes theorem. And this equation need to be valid for any region, any box I draw. Okay? For any box I draw, the two sides should be equal. If this equation should equal for any box I draw, then the only way to do that is to make sure that the partial rho partial t and the j are the same thing. Sorry, divergence of j are the same thing. So they should equal everywhere in the system. That's the only way to guarantee. No matter which region I choose to do the integral, they're always the same. And I'm sorry again if I missed the minus sign here. There should be a minus sign here. Okay. It should be the minus divergence of j. That's the same minus sign here. Sorry, I forgot. This is a typo. I will correct it shortly afterwards, after this lecture. So I forgot this minus sign. But nevertheless, this is a continuity equation. Okay, that's where the continuity equation comes from. Bottom line, the continuity equation is a very fundamental principle. Okay, it only requires two assumptions. One is charge conservation. We'd better have charge conservation, which at least we believe we have in ENM. Okay, if we don't have charge conservation, things will be really, really weird. We'll get some additional charge coming from nowhere. That's probably will not happen. We should assume that. Okay, and secondly is the principle of locality. Again, as I mentioned earlier on, we can't really prove our universe have to obey the principle of locality, but all the fundamental physics laws we know so far, at the fundamental level, they obey this principle. So these two principles are both fundamental principles that we shouldn't question, or there's no reason to question. And if we assume those two principles are right, then the continuity equation should be a right law of physics. Okay. So bottom line, continuity equation is not something happens to be true. It is really a fundamental principle that has to be true. Okay, so this is the continuity equation. Okay, so because the continuity equation is so important, it's so fundamental, this continuity equation better follow the structure we mentioned early on. Okay, we mentioned early on, if we believe all different reference frames are equivalent to each other, all physics laws should take the form of scalar equals scalar, vector equals vector, tensor equals tensor, etc. Okay, if this continuity equation is a fundamental physics principle, it should follow the same structure if we believe all reference frames are equal. Okay, does the continuity equation follow the same structure? Well, it turns out yes. Okay, first of all, the right-hand side is easy. Right-hand is just one number. It's 0. Okay, and it's always 0 in any reference frame. At least we believe continuity equation should be true for all reference frame. If we believe continuity equation is true for all reference frames, the right-hand side is obviously a scalar. It's 0 and it's never changed, so it's a scalar. Okay, if the right-hand is a scalar, the left-hand side must also be a scalar. Okay, and if we massage the left-hand side a little bit, the left-hand side can be written in this structure. Okay, it has derivatives, 4-dimensional derivatives, metric tensor, and another object of 4 components. Okay, this structure, if you recall what we learned earlier today, this structure is exactly the structure of an inner product of 2 vectors. Okay, this one is already a vector we know. Okay? This one is already a vector we know. That's a derivative vector. A vector times a metric tensor times another vector. If this guy, this column vector, this rho j, 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 if this guy is also a vector, then this whole thing is precisely the inner product of 2 vectors. And that's precisely a scalar. And the scalar equals 0 equals another scalar. That's exactly what we want. Okay. In other words, in order to make sure continuity equation follow the structure of scalar equals scalar, we have no other option. The only option here is to request this rho j, j, j is a 4D vector. This rho JJJ has to be a 4D vector. If it's a 4D vector, this whole thing gives me an inner product of two vectors. It's a scalar, so I have scalar equals scalar. If rho JJJ is not a vector, then this whole thing on the left-hand side would not be a scalar. If it's not a scalar, this whole equation, the continuity equation, will not obey scalar equals scalar structure. Okay? If it does not obey scalar equals scalar structure, it will mean that the continuity equation, or say charge conservation law, will change from one reference frame to another. That's something we cannot allow. At least that is not allowed by the assumption of Einstein. Einstein assumed all the reference frames are equivalent. If all the reference frames are equivalent, it means we have to assume zero speed of light and charge density and the current density, Jx, Jy, Jz, form a four-dimensional vector. Okay, so this has to be true. Otherwise, the reference frame, different reference frame, cannot be equivalent to be equivalent with each other. Okay, so the bottom line from continuity equation and this principle, all reference frame need to equal to each other. We immediately come to the conclusion this zero JJJ must be a 4D vector. Once we know it's a 4D vector, then immediately we know it need to follow the same transformation, same Lorentz transformation as coordinates. So if we change from one reference frame to another, the new reference frame, this rho prime, J prime, J prime, J prime must be related with the old reference frame rho JJJ by this Lorentz matrix in the middle. Okay, and gamma is 1 over square root 1 minus speed of light squared over velocity squared. Sorry, velocity squared over speed of light squared. Okay, the same gamma we defined in the Lorentz transformation. Okay, so the bottom line, without any additional assumptions, as long as we assume continuity equation should remain the same in all reference frame, we immediately figured out how charge current and how charge density and the current density should transform under Lorentz boost from one reference frame to another reference frame. Okay, and this is actually a very important principle. Okay, so you are coming in the homework this week. We will explore this transformation of charge and current density. Okay, and most important thing I would like to highlight here is that from this structure, we notice that charge density is not a scalar. Charge density is one component of a vector. It's not a scalar. Okay, so it's part of a vector. If charge density is not a scalar, but say part of a vector, it means charge density depends on reference frame. If you measure charge density for this region in one reference frame, then go to another reference frame to measure the charge density of the same region, we will come to the conclusion that charge density is changing from one reference frame to another. In other words, charge density is a quantity that we have to define for each reference frame. For different frame, it gets different value. However, as you will see in your homework, charge density is not a scalar, but the charge is a scalar. Okay? In your homework, you will show that because charge density is not a scalar, it's a component of a vector, we can actually prove that the integral, spatial integral of charge density, which is charge, is actually a scalar. In other words, charge does not change from one reference frame to another. So you probably already realized when we talk about special relativity, in any like fundamental physics or particle physics, even if the speed of the particle is very high in the special relativity in the relativistic regime, we never said charge in one reference frame. We always say charge of electron, charge of photon, charge of this particle, charge of quark, charge of this particle, charge of that particle. When we say the charge of a particle, we never emphasize which reference frame. Okay? The reason we never emphasize which reference frame is because charge is a scalar. Charge does not change when we do the Lorentz boost, when we change from one reference frame to another. And this is actually a very non-trivial physics because charge density is not invariant. Charge density actually changes from one reference frame to another. But after we do the integral, after we do a spatial integral and calculate the total charge of object, that one is actually Lorentz invariant. Okay, And I can briefly I give you the reason. The reason is because charge density and the charge, they are related by a spatial integral. And spatial integral is basically calculated the volume of area. Okay? And the volume of area change from one reference frame to another. Okay? For example, it's because of the length contraction, as we discussed earlier. Volume change from one reference frame to another. The spatial integral change. Charge also change. But magically, when we multiply them together, the multiplication actually don't. Okay, so the charge actually don't. So if we want a quantity which is conserved, it turns out the corresponding density cannot be a scalar. The corresponding density we want it to be the first component of a vector, and you will see this in your homework. Okay, so the last line here, if you want the covariant and contravariant language, the continuity equation in the covariant and contravariant language looks like this. Okay, the derivative, which we use a covariant derivative with lower indices, and the current we use the 4D current, we use this guy. That's a 4-dimensional contravariant vector. And when they multiply together, it's a scalar and a 0. So that's the continuity equation in the covariant and the contravariance convention language. Okay, so that's the continuity equation. Okay, so from continuity equation, we learned a lot about how charge, current, and charge density should transform under Lorentz boost, and how charge should not transform, should stay the same under Lorentz boost, as you are seeing in your homework. Okay, now let's look at Maxwell equation. Okay, we already figured out the transformation for rho and j. Okay, and then we can utilize Maxwell's equation to learn what are E and B. How do we organize E and B as 4D vectors, scalars, tensors? Okay, so this is precisely what we need. Okay, as you can see, one side of the equation is rho and j. It contains rho and j. Okay, rho and j we already know it gives me a 4D vector. Okay, that means immediately the other side of the equation also need to be a 4D vector. Okay, in order to make sure that all the reference frames are equivalent to each other. So utilizing Maxwell's equation, immediately we can learn how to organize E and B in terms of this scalar, tensor, vector, 4D scalar, 4D vector, 4D tensor structure. Okay, that's our goal here. So we will utilize Maxwell's equation, and part of the equation we already know, rho and j we already know, and we will use this equation to figure out the rest part. Okay, okay. But before we handle the Maxwell equation, it turns out that E and B are not the most convenient object to look at. Instead, we are going to utilize the vector and scalar potential. Okay, and the reason for that is because two reasons. First of all, E and B are too complicated. Okay, if we look at this Maxwell's equation, we have 3 components of E, 3 components of B. We have 6 degrees of freedom in total for each spatial point. Okay, that's a lot of degree of freedoms. Okay, 6-dimensional equation is not something easy to solve. And on top of that, these 6 degrees of freedom are not independent of each other. They're actually related. Okay, and to see that related, for example, we can look at this Maxwell's equation, the third equation in Maxwell's equation. For example, the 3 components of B, Bx and By and Bz, we cannot take Bx and By and Bz to be arbitrary values. We have to remember that there is a constraint between them. The total divergence needs to be 0. Which means if I already figure out Bx and I already figure out By, Z, I don't have much degree of freedom. I need to make sure that I need to choose Z such that this divergence is 0. Okay, so these 6 components are not independent. Too many components and they are not independent. So we need to solve these equations, and in the same time, keeping in mind there are some constraints we need to follow. That's a complicated beast. Okay, that's not convenient at all. Okay, it turns out mathematically there's a trick to make the same mathematical problem a lot easier to handle. That is to utilize the so-called potentials, or scalar potentials and the vector potentials. Okay, and the power of using potential, we already seen that power in, say, electrostatics. So in electrostatics, if we use E, if we try to solve E in all the, everywhere in our system, I need to solve 3 components, 3 functions, one for Ex, one for Ey, and one for Ez. Okay, and to solve 3 components at the same time. But if we instead using scalar potential phi, using the potential phi, electric potential phi, then it becomes a scalar problem. I just need to solve one quantity for each spatial point. And if you remember, if you recall in electrostatics, we always do phi. We always do the equation for phi. The Laplacian of phi equals to up to some constant charge density. And we solve that Laplacian equation. Okay, we never try to use E. And this is because phi is a lot easier to handle. We only need one component, one degree of freedom, and each space point. It's a much easier problem. Okay, and for E and M, for electromagnetic dynamics, it's the same story. Okay, if we use E and B, we need to solve for 6 components on each point. But if we choose scalar and vector potential, we only need 4. Scalar potential, AX, AY, AZ. Okay, 6 to 4 is a lot of simplification. Okay, so that's a mathematical trick we're going to follow. So the first, we will convert the equation for E from E and B to A and phi. Okay, so this part you already learned it in E and M 1. So I will just quickly remind you about scalar and vector potentials. Okay, so first of all, let's define vector potential. The reason we can define vector potential is because B is divergence free. Okay, divergence of B is 0. If divergence of B is 0, we can prove mathematically B can be written as the curl of a vector field. That vector field is what we call vector potential. Okay. Mathematically speaking, this statement is not quite right. Okay, so divergence free does not mean necessarily you can write it as a curl of another field. Mathematically, we need 2 conditions. One is divergence to be 0, and the second condition is we need to assume our space is singly connected. In other words, there's no holes in our space where we cannot enter. Okay, I will not go into much detail, but nevertheless, for our universe, we usually assume our universe is singly connected. It's a simple structure. There's no this hole and to cause us any trouble. So in that situation, we can prove that magnetic field indeed can always be written as the curl of another object, and that object is vector potential. Okay, so the bottom line, in addition to divergence being 0, we also need some assumption about the space. But usually we assume our universe is simple, the space is simple. If it's simple enough, then this is always true. Okay, but there are exceptions. If our space has some special properties, this will not be true. Okay, but nevertheless, for the simplest setup, for the simple space, we assume this is always true. For any magnetic field, we can write it as a curl of vector potential. So that's the definition of vector potential. Okay. So once we define the vector potential, the next step is to look at the second equation of the Maxwell. Okay. So this second equation, we can move B to the other side. If we move B, time derivative of B to the other side, it becomes this. 0 equals the curl of E plus time derivative of B. Okay. So it's the same equation. I just move B and E to the same side of the equation. And here, because B, we already assumed we already showed that B is the curl of a vector potential. We replace B by the curl of a vector potential. And now we have curl of E and the curl of A and then time derivative. We can take the curl together. Okay, we can pull the common factor, which is the curl, and rewrite these 2 terms as curl of E plus time derivative of A. Okay. So in this language, once we introduce vector potential, we immediately prove that the second equation of Maxwell is curl of this whole thing equals 0. Okay, curl of something equals 0 means this object, if vector field, its curl is 0, it's curl free. Then it means we can write this object as a divergence of the scalar. Again, mathematically, this is not quite right. We still need to assume the system is singly connected, but we always assume our universe is singly connected. So this is true. Okay, so this curl-free condition means we can define a scalar field phi, and the gradient of this scalar field, and the convention is put with minus sign here. That's just a convention. The gradient of this scalar field is E plus time derivative of A. Okay, so we can always choose a field phi such that this is valid. Okay. In other words, we can write electric field as time derivative of A minus time derivative of A minus the gradient of phi. Okay, so that's the definition of scalar and the vector field. So for magnetic field, it's just the curl of the vector field. For electric field, it's a little bit more complicated. It's a time derivative of vector field and also at the same time, the spatial gradient of scalar field. Okay, if we are doing electrostatics, if we're doing electrostatics, there's no time derivative. Everything is static. Okay, static has no time derivative. Then this recovers the electric potential. Gradient of electric potential is electric field. But in E&M with dynamics, we need this additional term of time derivative of A. Okay. Nevertheless, with A and phi, with scalar and vector potential, we can prove that as long as our universe is singly connected, as long as the space has nothing, no strange structures, we can replace B and E by A and phi. Okay? If we know A and phi by taking derivative, we immediately know B and E. And one nice thing about, actually there are two nice things about this A and phi language. First of all, it captures all the same information, but with much less components. A and phi only has 4 components on each spatial point: phi, ax, ay, az. That's much better than ex, y, z, bx, y, z, 6. Okay, so we reduced our unknown from 6 to 4. That's one advantage. And the second advantage is once we write down this vector and scalar potential, we don't need the middle two Maxwell's equation anymore. These middle two equations automatically satisfied when we define A and phi, when we define vector potential and phi. Okay, we got 2 less. We reduce the number of degree of freedom by 2. Okay, from 6 to 4. 6 components now become 4 unknown components. Okay, that's reducing the unknown numbers. And at the same time, we also reduce the number of equations. The middle 2 sets of equations we don't need them anymore. It's automatically satisfied as long as we define A and phi. Okay, we only need the first equation and the last equation. That's great. Okay, so we reduce the number of equations, we reduce the number of unknowns, everything becomes a lot simpler. Okay, so then we replace E by this thing, and replace B by the curl of A, and plug them into the first equation of Maxwell's equation and the last equation of the Maxwell's equation. Okay, and with A and phi replacing E and B, those 2 equations become these 2. Okay, this we already learned in E&M1. I will not show into detail. And if you are interested in, want to remind you yourself about how these equations are obtained, we just need to look at the corresponding chapters in E&M1. Okay, so bottom line, once we use E and phi and A, scalar and vector potential, the equation become a lot easier. Okay, we remove the 2 sets of equations. We are not used. We don't need them anymore. And the unknown also becomes easier. We only have 4 unknowns on each point. Okay. And this derivative, this partial differential equation of Maxwell now becomes a second-order derivative equation. Okay, in terms of E and B is first order. But because when we convert E and B to A and phi, we need another derivative. So this becomes second-order derivative equations. Okay. And these equations are something that we are quite familiar with. Look at this derivative. There are time derivatives minus spatial derivative, second order. This is exactly the scalar derivative, scalar second-order derivative we showed earlier. The derivative vector inner product to itself gives us a scalar. And we show that scalar is a second-order derivative, which is precisely this object. Okay, so we can rewrite these derivatives in this square symbol. The square symbol means a second-order derivative, which is a 4D scalar. We already know. Okay, so we can rewrite these 2 equations into this. The derivative is a 4D scalar, and then derivative acting on phi, derivative acting on A. The other side of the equation is charge density and current density. Okay, now let's make one more massage for this formula. Okay, we have 2 sets of equations. This one comes from the first equation of Maxwell. This one comes from the last equation of Maxwell. The middle 2 we don't need them anymore. Okay, we can combine these 2 sets of equations together into a vector, a 4-dimensional vector. Okay, and in order to do that, so first of all, we can realize there's one equation here. It's just equation for phi, but there are 3 equations here: one for ax, one for ay, one for az. Okay, because A is a vector. And we write, so 1 equation, 3 equation, we combine this 1 and 3 equation together and the 4 equations. Okay, So when we combine these two sets of equations into this 4-component equations, we made a small trick. The small trick here is for the first equation, I divided speed of light c on both sides of the equation. Okay, and by dividing the speed of light c on both sides of the equation, there are two nice things about this additional factor 1 over c. First of all, you can check the unit of scalar and vector potential, and in the SI unit, you can realize immediately by dividing the speed of light c, now these 4 objects have the same unit. Same is true for the charge density and current density. By dividing the speed of light, these 4 objects now have the same unit. Okay, so that's very nice. It makes the unit consistent. And all the 4 equations have the same unit now. And more importantly, if we look at the right-hand side of the equation, after multiplying this one additional factor 1 over c, the right-hand side of the equation is precisely the 4D vector we defined earlier, we learned earlier. Okay, so in the previous sector, by looking at the continuity equation, we realize that in order to make sure the continuity equation is invariant in different reference frames, all reference frames see the same continuity equation, we have to come to the conclusion that charge density and current density form a 4D vector like this. And by adding this 1 over c factor, it gives us precisely the 4D vector. That's the most important reason why we need this 1 over c factor here. Okay, so let me highlight a couple other things. Okay, so first of all, when I write down this equation, for the right-hand side, I put a common factor mu0 out. Okay, so there is this mu0 factor for each j, so I put that out. Because I put this common factor mu0 out, I need to add a 1 over mu0 factor for rho. There was no mu0 here. If I want to put the mu0 out, I need to add 1 over mu0 to balance that for the rho component. Okay, and that is actually very nice because if you look at this first component here, epsilon 0 mu0, by definition, it's 1 over speed of light square. Epsilon 0 mu0 is 1 over speed of light square. And we have another speed of light here, and this speed of light cancels one of this 1 over c square, one of the speed light here, and eventually we get 0. Okay, that's where this speed of light c comes from. And at the end of the day, this whole thing becomes a 4D vector. And this is the same 4D vector as we show in the previous section. Okay, so from continuity equation, we know this must be a 4D vector. And now from Maxwell's equation, okay, if we want the Maxwell's equation to be the same in different reference frames, we have to assume Maxwell's equation also obeys the structure we discussed earlier. Scalar need to be equal to scalar, vector need to be equal to vector, tensor need to be equal to tensor. Okay, the two sides of the equation need to have exactly the same objects, same type of objects. The right-hand side is a 4D vector. We already know that. This means immediately the left-hand side must also be a 4D vector. Okay, and how can we make this left-hand side a 4D vector? First of all, this square is a scalar. Okay, if we want a scalar times something to be a vector, the only way to do that is this whole thing is a vector. Okay, so the only way to make sure that Maxwell's equation satisfies this vector equals vector structure is to accept the fact that this phi over c, scalar potential, and the vector potential ax, ay, az forms a 4D vector. That's the only way to make the equation Lorentz invariant. It's the only way to make sure Maxwell equation stays the same in different reference frames. Okay, so from the Maxwell's equation, we come to the conclusion, these 4 objects need to be a 4D vector. If these 4 objects is a 4D vector, then immediately we know the Lorentz boost of phi and a, okay? Because the 4D vector under Lorentz transformation, the transformation is exactly the same as coordinates. So this is a transformation, Lorentz transformation for time x, y, z. So scalar and the vector potential must follow exactly the same transformation. Okay, and in physics literature, at least in some literature, people define A0 as phi over c. So scalar potential divided by speed of light, we call it A0. Okay, if we call this one A0, then this full vector is just A0, A1, A2, A3. Okay, and similarly, in many physics literature, we call speed of light times charge density to be J0. J0 is 0. Okay, we call it J0. And if we use that convention, then the Maxwell's equation is this. Okay, You have a scalar, which is second order derivative, times a vector, that gives me a vector, equals to mu0 is also a scalar. It's a phase constant invariant under different, in all reference frames, and times a vector. That's the current and charge density and the current density vector. And this Maxwell's equation indeed follow the structure of vector equals vector. Okay. If you want to use the covariant and the contravariant vector convention, then the Maxwell's equation, the same Maxwell equation, is usually written in terms of like this. Okay, and A mu and J mu, they are both super indices. It means that these two are the contravariant vectors, what we call vectors, contravariant vectors. And the second order derivative and mu0, they are two scalars, and scalar times vector equals vector equals another scalar times vector, which is another vector. Okay, I think right now is a good point to stop. So today we finished our discussion about mass. Okay, and from the mass part, we come to the conclusion: if we want our fundamental physics laws to remain the same in different reference frames, okay, in other words, if we want all the reference frames to be equivalent to each other, then we have to make sure that our physics law takes the form of scalar equals scalar, vector equals vector, tensor equals tensor. Okay, and then in the third chapter, as we did here, we applied this principle to two equations so far. First, we applied this to the continuity equation. Okay, so from the continuity equation, we come immediately to the conclusion. This guy is a 4D vector. And for Max, then we do the same thing for the Maxwell's equation. For Maxwell's equation, if we want the Maxwell equation to obey this vector equals vector structure, we immediately come to the conclusion: scalar and vector potential together, combined together, gives me a 4D vector. And once we realize these are 4D vectors, how they should transform under Lorentz boost is obvious. Okay, they have to follow the same Lorentz transformation as coordinates. That's the only way to make sure that all my equations, all my physics fundamental laws stay the same in different reference frames. Okay, and in the next lecture, we will continue with this same trick and apply the same trick into other physics equations. And eventually, we will come to the conclusion that energy equals to mc squared. Okay, by keep doing this for the physics laws, we know eventually we will reach the conclusion energy equals to mass times speed of light squared. There's no other option. That's the only way we can maintain, we can make sure that all our physics laws stay the same in different reference frames. Okay, I think this is a good point to stop. And next time we will continue our discussion, and the immediate topic in the next lecture, we'll talk about the gauge choice. Okay, I'll see you next time.